In this lesson, we're going to cover joint probability and the multiplication rule. So the joint probability for two events is simply the probability that A and B occur at the same time. That's what we call a joint probability. Now, if you think back to the addition rule evaluated the probability of A or B. And in the evaluation of this, we had to evaluate the probability of A and B at times, but they were fairly easy probabilities to evaluate. Sometimes it's a little bit tricky to evaluate the probability of A or B, and so that's what we're going to go over in this lesson. Now to start, let's consider this simple example. This is going to illustrate how the multiplication rule works for evaluating the probability of A and B. So in this example, what we do is we first flip a coin and then we roll a die. We want to calculate the probability of getting heads and a 5. So we want to calculate the probability of this. Now when you read this, it means you get a heads when you flip a coin, and then you get a 5 when you roll the die. So there's really like a little hidden then in between the and the 5. This is called a joint probability. So to solve this problem, consider this tree diagram that we have down here. This is going to help us to enumerate the sample space for this experiment and calculate the probability. So in this tree diagram here, the first thing you do is you flip your coin. Well, when you flip a coin, you can either get heads or tails. Now if you get heads, you then roll the die. You can get a 1, 2, 3, 4, 5, or a 6. So these are some outcomes that you can get for the experiment. You can get heads 1, heads 2, heads 3, heads 4, heads 5, and heads 6. Now if you flip the coin and you got tails, well, you can also get then, when you roll the die, a 1 through 6. So you can get tails 1, tails 2, and so on out through tail 6. So the sample space for this experiment would look like heads 1, or getting heads and then a 2, or getting heads and then a 3, and so on, out through tails and a 6. So we see that there are 12 possible outcomes for this experiment. Each branch of this tree diagram represents one possible outcome, and there are 12 total branches. You see, you have 12 listings here along the very bottom row. Now each of these has the same likelihood of occurrence. The probability of getting heads and a 4 is the same as the probability of getting tails and a 2, as long as the coin is fair and the die is fair. And we see that getting a heads and then a 5 is one of those 12 possible outcomes. So the probability of getting heads and a 5 is 1/12, and that's our answer. Now that's not the end of the story here. You see, we want to find an easier way to calculate this than going through this tree diagram. That's what the multiplication rule is going to do for us. Well, up here, take note that this 1/12 can be written as 1/2 times 1/6. And it's interesting to note that the 1/2 is your probability of getting a heads when you flip a coin, and the 1/6 is the probability of getting a 5 given that the heads occurred first when you roll the die. Now, you might wonder why we use this conditional probability here. This 1/6 is just the same as the probability of a 5 when we roll the die, but this is going to come up in the multiplication rule as we'll see later on. So these are really the same, probability of a 5 and probability of a 5, given that heads occurred the first time, because they're independent events. But just go with this for the moment. So we see that The 1/12 is really probability of getting heads times the probability of getting a 5. Now, is that a coincidence? No, that is always going to happen, and that's called our multiplication rule. We evaluate the probability of getting heads, multiply it by the probability of getting a 5, and that's our probability of getting heads and a 5. That's how the multiplication rule works. So let's take a look at the multiplication rule here in our next slide. So here's a full statement of our multiplication rule. So to calculate the probability of A and B, we can evaluate it as the probability of A times the probability of B given that A occurred previously. Or we can actually flip these around and write it as the probability of B times the probability of A given that B occurred first. Now, if the events A and B are independent, then the probability of B is the same as the probability of B given that A occurred, in which case our multiplication rule becomes this right here. But I recommend that you use the general rule of multiplication up here because this always works. If A and B are independent as you're working through these problems, you'll just evaluate this as the probability of B anyway, and it all just works out. So I recommend just using the general rule up here. Also note that if the events are not independent and you use this rule here, well, then you'll get the wrong answer. So I recommend that you always use this rule here, the general rule. Now, in our previous problem that we just looked at, when we're evaluating the probability of getting a heads and a 5, you notice that the probability of getting a 5 was the same as the probability of getting a 5 given that a heads occurred previously, because those events were independent. Flipping the coin and rolling the die, the coin flip has no bearing on what occurs when you roll the die. So those events were independent. So in the previous example, we were actually using the special rule right here for multiplication. But we used this one anyway. And it all worked out just fine because the probability of a 5 is the same as the probability of a 5 given heads. Now we're going to take a look at a few more examples. And down here note that we have a graphical explanation for why the multiplication rule works. You can read through that on your own. And as we're working through our examples, you'll get a better understanding of why this rule holds. So in this example, a golfer has 12 shirts. And suppose that 9 of the shirts are white and all the others are blue. So he has 9 white shirts and 3 blue shirts. So he gets dressed in the dark, he just grabs a shirt and puts it on, and he plays golf 2 days in a row, and he doesn't do any laundry. What is the likelihood or probability that both shirts selected are white? So that's just like reaching in your closet, grabbing one shirt, grabbing another shirt at random, and you want to know what's the probability of getting a white shirt on day 1 and then a white shirt on day 2. Well, by our multiplication rule, it's going to be the probability of getting a white shirt on day 1 times the probability of getting a white shirt on day 2, given that you previously selected a white shirt on day 1. So the probability of getting a white shirt the first time you reach in the closet and grab a shirt is 9 out of 12. Now once you do that, you took one shirt out, so now you only have 11 shirts left. 8 of them are white and 3 of them are blue. So the probability of getting a white shirt on day 2 is then going to be 8 out of 11. You see, once again, because you took a white shirt out, you only have 11 shirts left with 8 of them being white. So by the multiplication rule, our probability is going to be 9/12 times 8 out of 11. And when you evaluate that, you get 0.55. So you see we needed to write our probability in this manner. In this case, the events are dependent because you did the experiments without replacement. Now let's take a look at another example. So in this problem, we have a bin that contains 10 balls numbered 0 through 9, and we randomly select 2 balls from the bin. What is the probability of drawing a 3 and then a 5 in this order? And we also have some conditions here. If the drawings are made, part A, with replacement, so in other words, you draw the first ball out of the bin, write down its number, put it back in, shuffle them around, and then draw the second ball. And then part B is, what if we did it without replacement? So we draw the first ball out of the bin, look at it, put it aside, and then draw the second ball out of the bin and note its number. So we want to calculate the probability of getting a 3 and a 5 in both of these cases. So for the first part, part A, the probability of a 3 and a 5 is going to be, by the multiplication rule, probability of a 3 times probability of a 5, given that a 3 was previously drawn. Now the probability of getting a 3 the first time is 1 over 10. And the probability of getting a 5, given that a 3 was previously drawn, is also 1/10. That's because we put the ball back in the bin. So you see this part right here is really just the probability of getting a 5 because the events are independent. You put the first ball back in the bin before you took the second ball out. So both of these probabilities are 1/10, and when you multiply them you get 1 out of 100. Now let's take a look at the second part. Here we do not replace the first ball when we draw the second one. So in that case we still follow the multiplication rule. Probability of a 3 and a 5 is going to be probability of a 3 times probability of a 5, given that a 3 was previously drawn. Now the probability of a 3 is 1/10, but the probability of a 5 has changed. It's actually 1/9 because the bin no longer has the number 3 ball in it. You only have 9 balls left, and one of them is a 5. So your probability of getting a 5 is now 1/9. So you see it changed. The events became dependent because you didn't replace the first ball. So our probability is 1/10 times 1/9, and that is 1 over 90. Let's take a look at another example. Now for this example, we're going to do a slight variation of the previous example. We have a bin containing 10 balls numbered 0 through 9, and we randomly select 2 balls from the bin without replacement. We want to find the probability of drawing a 3 and a 5 in any order. So the probability of getting a 3 and a 5 in any order is going to be the probability of getting a 3 and then a 5, or a 5 and then a 3. So by the addition rule, you see this word or right here. So by the addition rule, this is going to be the probability of a 3 and then a 5 plus the probability of a 5 and then a 3 minus 0. Now that 0 comes from the addition rule where you subtract the probability of A and B. Now in this case, that's going to be the probability of getting a 3 and then a 5 and a 5 and then a 3, which of course is 0 because that can't happen. So our probability up here, let's note that the probability of a 3 and a 5 is 1 out of 90. And the probability of a 5 and a 3 is 1 out of 90 as well. And so the probability of getting a 3 and a 5 in any order is going to be 2 over 90, where we sum the two probabilities of 1 over 90. So you see, when you apply the multiplication rule, you have to be a little careful because the probability of A and B really means the probability of A and then B occurring in many of our experiments. Now let's take a look at this example that incorporates the multiplication rule and the complement rule. Now here's a tip that I recommend you follow. Anytime you see the wording at least one or more in a problem, that's an indication that you may want to use the complement rule that we have down here. So this is just a different variation of the complement rule. If A is the event of getting at least one of some event occurring, then the complement of A is going to be where you get none of those events occurring. So that's going to be A complement. So you see, this is just a different way of writing the complement rule. Let's take a look at this example here. So in this example, we have a coin is flipped 4 times. We want to find the probability that in the 4 flips, at least one tail appears. Alright, so we see the wording at least one. That indicates that we want to use this version of the complement rule here. So we're going to let A be the event of getting at least one tail. So then what's the complement of A going to be? Well, that's going to be the event that in the 4 flips we get no tails or all heads, right? So A complement, the complement of getting at least one tail is getting all heads in the 4 flips. Okay, so that's what we have right here. So this is what we want to find, the probability of getting at least one tail in the 4 flips. So that's going to be 1 minus the probability of getting all heads in the 4 flips. Now we just need to calculate this. As we'll see, this is fairly easy to calculate, and then we'll have our answer. So right here we have the probability of A complement, which is the probability of getting all heads. Now that's the same as getting heads and heads and heads and heads when you flip a coin 4 times. Now by the multiplication rule, well, before I do the multiplication rule, just note, you see the word and here. That means we're going to be multiplying. If you had the word or here, that would be the addition rule, right? So this is going to be the multiplication rule. So the probability of getting heads, the first flip is 1/2. And then we multiply times the probability of getting heads the second time. That's going to be 1/2. Heads the third time, that's going to be 1/2. And heads the 4th time, that's going to be 1/2 as well. So when we multiply all these together, we get 1/16. So 1 out of 16, that's the probability that when you flip a coin 4 times, you get 4 heads appearing. So then the probability of getting at least one tail is going to be 1 minus the probability of getting all heads. So that's going to be 1 minus 1/16 or 15/16, and that is our answer. So this is the probability of getting at least one tail when you flip a coin 4 times. Now just notice one thing here. When we did the multiplication rule up here, we really used a special case of the multiplication rule where the probability of A and B is the probability of A times the probability of B. Now the regular multiplication rule is B given A. But in this case, when you flip a coin, those are independent events. So this is just the probability of B right here. So this would be like the probability of getting heads and heads when you flip a coin. That's going to be the probability of getting heads the first time times the probability of getting heads the second time. What happened on the first flip has no bearing on what happens the second time, so we use the special case of the multiplication rule here when the events are independent. That's what we did right here. And so that concludes this discussion of the multiplication rule.